All right. Oh, thank you. Hi, everybody. Thanks for coming to Colloquium. Today's speaker is Sofia Ramstedt. Sofia Ramstedt is visiting us from Uppsala University, where she is an assistant professor and senior lecturer. Before that, she did her PhD at Stockholm University, and she also did her undergraduate degree there and spent some time in Bonn on a postdoc. I started collaborating with Sofia maybe 5 or 6 years ago, looking at crazy things from AGB stars like X-rays and UV emission, which we didn't expect to find, but we found. Sofia is going to talk to us today about some Alma observations of stellar winds, mostly sun-like stars, not too many massive stars. I don't think any massive stars at all. One interesting fact about Sofia I wanted to share with you all is that she got me into crocheting. And the very first thing that I crocheted after she taught me how to, or she showed me how to do it, is this crochandra. It's got the solar shade, sunshade, and everything. So with that embarrassing anecdote, I think I'll turn it over to her.
I think it's a very good job. Okay. Right, so thank you for that, Rudy. I will start out by giving you quite a lot of background. I will talk about, like Rudy said, low mass stars, and these are now stars that are evolved, so stars that are on the AGB. Now the AGB community can be divided research-wise into looking at different parts of the star. So some people are working on the interior, some people are more interested in the stellar surface. In Uppsala, we do a lot of wind and the circumstellar envelope and ISM interaction. And all these different regions, of course, have different probes. So for the interior, what happens in the interior can be probed mainly by surface abundance changes. Seismology is not easy for these pulsating crazy stars. So there has been attempts at doing it, but nothing has been very successful so far. And what you're trying to study when you're interested in this is nucleosynthesis and the mixing inside of the star. I will not spend more time on the interior, but I will instead spend some time on talking about the stellar surfaces. This has been enormous observational progress when it comes to looking at the surfaces of these stars in just the last 2 or 3 years or so, with new instrumentation and new facilities at VLT mainly. And also on the theoretical side, the models have also developed a lot during the last couple of years. And these are done by colleagues of mine, the models in Uppsala. So I will show you some recent results from these models. Okay, so the wind is also modeled at my department in Uppsala. The models are called Darwin models. These are radiation hydrodynamic models, and they include grain formation and growth. So you solve the wind formation from first principle. You only need to put in the stellar parameters, and out comes the wind. If you want to constrain these models with observations, trying to observe the wind-forming region is difficult. There's not a lot of probes there, so what we do instead is that we look at the circumstellar envelope, and this is my own area of expertise. This can be probed either with molecular line emission or with dust emission. So this I will also spend some time on. Finally, there are people looking at interactions with the ISM as well, but mainly to understand something about what constrains the distribution of the wind and so on. But this is also not something that I will have time to get into today. So this gives you something about the physical scales that we are talking about. So at the center you have the star. It's about 1 AU in radius. And the surface temperature will be around 3000 K. And then you have a thin region where the wind and dust is formed. And then radiation pressure on the newly formed dust grains will push them out. and momentum transfer between the dust grains and the gas is what causes the wind. And over time, the wind will build up this huge, thin circumstellar envelope. So as you can see, this region here is quite thin. It's about up to maybe 10 stellar radii or so. And then the rest is this huge circumstellar envelope. So if you have resolved observations, you can probe the mass loss rate history by looking at this. Or if you have unresolved observations, what you will get is an average over time instead. All right. So AGB stars come in 3 different flavors. You have the normal M-type stars, where you have more oxygen than carbon. Then there is an intermediate type called S-type, where we think that they have about the same amount of carbon and oxygen, probably a little bit less carbon than oxygen. For solar masses, if you're a star heavier than 4 solar masses, the carbon gets destroyed, and then it will be an M-type star. Right. This is a pretty picture of how how this happens. So for the carbon stars, this is not getting a wind going is not a big problem. The carbon grains can absorb a lot of radiation from the star, and it just goes off, and then you have a wind. For the M-type stars, it's been a bigger problem because they have a lower condensation temperature, the silicate grains. So it's difficult to form the grains at the right distance from the star, so you can get a wind. But this has been solved now by including scattering in the models, because then you can get the grains forming, they won't heat up as quickly, and they can form closer to the star. So we have models now that can produce mass loss in both M-type and carbon stars. All right, so how do we measure this wind? So there are 2 ways of measuring mass loss rates from AGB stars. The more reliable one is to use CO rotational transition line emission. So the circumstellar envelope consists mainly of molecular gas, and then it's about 1,000 in mass ratio to the dust. So that is why you want to prefer using the gas as a probe. By doing several transitions, you can cover the full range of the circumstellar envelope. So you do the lower transitions will cover the outer part. This is the radius in years. So this is the creation lines. So this is typical observations that we have. This is what it looks like for a optically thin case, and this is for an optically thicker case. Now, you can only do these type of observations for nearby stars because it becomes too weak, and also you don't have the resolution to resolve individual stars in the radio submillimeter regime. So as soon as you want to go outside of our own galaxy, then you have to resort to dust, probing the dust emission instead, and you do that by observing photometric points along the SED, essentially. So shorter wavelengths will probe the stellar contribution, and then you will have contributions from warm dust and cold dust in different parts of the SED like this. And these are probed by, you just collect a lot of data from different instruments, and then you can step out the whole SED. All right. So this is what the results look like for from CO observations. So these are galactic stars. Mass loss rates range from a few times 10 to the minus 8 up to a few times 10 to the minus 5 solar masses per year. The different colors are the different chemical types. So carbon stars are red, M-type stars are blue, and S-type stars are green. These are the velocities. they range from just a few kilometers per second up to 30. So for the mass loss rate distribution, we don't see much of a difference between the chemical types, but we see a trend that the carbon stars have slightly higher velocities, which is not surprising because it's just more efficient wind driver, the carbon grains. And this is how, if you plot them against each other, how they relate to each other, mass loss rate, velocity. And this is what we use to constrain the wind models. So now if we look at what the models can do, here we have mass loss rate distributions for M-type stars. Different pulsational types are the colors here. It's not so important, but what you can see is that this gray area is what the models can do, and they cover the full range of the observations essentially. So for M-type stars, the models are now very successful in reproducing the observations that we have. And this is for carbon stars instead. Here they tested going to LMC metallicities as well. And again, this will be the solar metallicity range covered by the models. And here they're actually not quite as successful because they cannot reproduce lower mass loss rates with the carbon star models. So this is a problem that they are working on and trying to solve, and hopefully will do so eventually. This is interesting plots for people who are trying to do mass loss rates from the dust, because to calculate a total mass loss rate from dust observations, you have to know the dust to gas ratio. And the most recent model results show that they are quite a lot larger than what has previously been assumed. So usually you will assume a gas to dust ratio of about 200, but it turns out that it's more of the order of 1,000, which makes an enormous change for any mass loss rate estimate that has been produced for an AGB star beyond our own galaxy. So this is important, and this is also what we see in the few observational constraints that we have. We also see this tendency. So this might have a big impact. So to summarize what we know for the wind, so the measured mass loss rates, they are about, on average 10 to the minus 7, 10 to the minus 6, and velocities are low. And we see a correlation that are similar for all three chemical types. From the theoretical side, we can now produce reasonable wind parameters for M and C-type stars, but there are no S-star models available yet. The models are available for limited range of stellar mass. They just recently did step away from having a star of 1 solar mass, so now they have a little range around 1 solar mass. And they have also started changing the metallicity, but that is also very recent work that is just about to come up on AstroPH, like this week or something.
Today?
Yes, today.
It's there. Oh,
Yeah,
yesterday.
yeah. All right, and then the most important thing is that the gas to dust ratio seemed quite a bit larger than previously assumed. This is interesting, like I said, because if we start to move outside of our own galaxy, this will have an impact on the mass loss rate that we estimate from these stars. The only CO observations of extragalactic AGB stars that exist came a couple of years ago, where we managed to resolve individual stars in the LMC with Alma. And it gave us estimates of a couple, like it's 5 stars, I think. And they're all very high mass loss rate sources, so that it's in no way representative of the full population or so. It's just the ones that were bright enough for us to be able to detect them. And we see from this, we think that we see a hint of maybe that you have a different dependence on the mass loss rate compared to the expansion velocities. But of course, with 5 sources, this is really nothing that we know by now, but it has to be followed up. All right. So that was some background for you, and now I will move on to talk about some recent observational results. So, okay, the top row here shows you VLTI, so infrared interferometry observations of a nearby AGB star where we have resolved the stellar surface. And the 3 different images shows you different wavelengths. So this is 1.625, 1.678, and 1.730 microns. So it's all pretty close together, wavelength-wise. Yeah, the scale of this whole thing is about 5 AU. So this is one of the nicest examples that we have of a surface like this. Of course, to do these types of observations requires a nearby star. So this can only be done for like a handful of sources now. These 2 examples, this one and this one, shows you a little bit larger scale images. This is with sphere on VLT. So this is now not interferometry, but imaging. And the size of the star is this white ring in here. So what you see is gas distributed around the star, close to the star. And this one shows you Myra with Alma. So at 332 gigahertz, it's about 850 microns, an image with the long baselines on Alma. So this is like the best resolution that you can get with Alma. And you can see how it's stretched out. The radio photosphere is slightly stretched out toward the direction of the companion, which is on that side over there. All right, so these observations are making us super enthusiastic in Uppsala, because it gives us the opportunity to constrain models that my colleague Bernd Freitag has been working on for many years. So this shows you now a beautiful movie of his 3D hydro model. It shows you the surface intensity of an AGB star and how it changes over time. So you have a time axis up here. And you can see how it comes and goes and moves around and bubbles and looks very beautiful. This is also the explanation why Gaia doesn't really help us out, the AGB people working in the galaxy, because as you can see, the photocenter of the star jumps around everywhere, and there is actually a paper out from last year that discusses this and shows that it's not going to work to do parallaxes on these stars. On the other hand, you can maybe use Gaia to constrain these movements instead over time. Yes, so he does these models. This is the whole star in a box. The latest development for these models are to include dust formation. So this shows you the density distribution. So the previous one was just surface intensity. Now this is density. This is what happens when the star has these huge convection cells moving out, and it flings off material like this. And then these 2 movies here shows you essentially the region where the conditions for dust formation is fulfilled. So depending on temperature and density, you form dust of different kinds at a certain radius. So this is corundum, and this is forsterite dust grains. This is the way we think that it happens in the M-type stars, that you first have corundum dust forming closer to the star, and then forsterite can grow on top of these grains. So this is the latest development when it comes to the 3D. They don't have wind yet, these models. We just have, but we have gas and dust formation, and the next step will be to calculate radiative pressure in these models as well. What we've been doing in the meantime is that one of our students, Sofia Liljegren, has put together the two models that we have. So we have these 3D models of the star that you just saw the pretty movies of. And then we have the wind models, which are all 1D. So she has tried to parameterize what happens at the edge of these 3D models, and then that can be used as an inner boundary to the wind model. So then you can see if you have these 3D effects with the whole thing going irregularly from one side to the other, what will that do to your wind properties? Usually what they have as an inner boundary condition for these 1D models is just like a smooth sinusoidal variation like this in luminosity and radius. And these are her results. So you have time here, and then you have mass loss rate and velocity here. And the gray line is what you get when you have the smooth variation at the inner boundary, and the green and red ones are what you get when you have more random variations that are derived from the 3D models. And it turns out that it makes quite an important, quite a significant difference. So you have 2 orders of magnitude variations, episodic variations in the mass loss rate, and a factor of 2 in the wind velocity, which makes quite a difference to the density. And when you have the faster wind slamming into a slower wind, you can get even more pileup. And we think that it might be able to explain some of the arcs and features that we can see in circumstellar envelopes of AGB stars. Right. But this is shaping of the circumstellar envelope on a rather small scale. If you do unresolved observations of this, you will not detect these types of observations. So what I've been working on for the last couple of years, and with Rudy as well, is to look at how you get large-scale shaping. So this will by this we try to explain how we can form the shapes that we see in planetary nebulae. So that is one thing that we were looking at. So I looked up Wikipedia, because that's where all information is. And this is the image that it has on how an AGB star is transformed into a PN. And it looks very round and wonderful and beautiful. But when we look at HST images of planetary nebulae, we know that this is not what they look like. We have bipolar structures, we have like bubbles and things flowing out in all different directions. So this has been a very big topic for the last couple of years, and also before that, trying to understand how these shapes can be formed from a round AGB star. So the idea that goes back for some years now is that you have something like this. So you have the old wind, the wind of the AGB star expanding from the star. And for some reason, which we don't understand, you have a thicker density along the equator. So you have a thicker layer of material along the equator like this. And then, again, for a reason that we don't understand, you set up a faster wind inside of this bubble, and it will have an easier time escaping in the pole direction, because it's just too thick on the sides. So this is called the generalized interacting wind model, and it can explain the formation of bipolar planetary nebulae. So what do we see when we look at the circumstellar envelopes? Do we see something that looks like it's going to turn into a planetary nebula? So I will show you some pretty pictures from Alma now. So this is LL Peg, and this is L2 Puppies. So these are two nearby AGB stars. And what we see is a lot of spirals, we see a lot of arcs, and we see some disks and some tori. R Scriptoris is another one that we did some years ago. This shows you just the center velocity image of this. So this is if you could do a cut through the star at the stellar velocity, you would see this. This is another star, and here we're stepping through the velocities. So you're going in on the front side and out on the back. So this is the same type of structure that this has as well. But this has also these arcs inside. So this is like a huge football, soccer ball, I don't know, a round ball that has nothing inside. And then this one is more like an onion. You have to imagine like an onion with like arcs and stuff. So the idea, when we observed R Scriptoris, which was one of the first projects that were done on Alma actually, was that we were interested in this shell because we think that the shell is created by a thermal pulse. So the star, as it evolves, has thermal pulses. The thermal pulse releases a lot of energy. Luminosity has a peak. This leads to a peak in the mass loss rate, and this creates this thin shell. The stuff that is inside, we were completely not expecting. But we think now that we understand where it comes from. And it's taken us until last year or 2 years ago to get a star where we can study only the shell. So that was nice. Okay. But so this arcs or spirally shape, and also the one that I showed you before, this one, can be understood if the star has a binary companion. So as the wind is flowing out from the star, you have a binary companion circling around it, and this creates this spiral density wave through the circumstellar envelope. But we know nothing about, we did not expect R Scriptoris to have a companion. We have searched for it now. We cannot see it. It's very difficult to detect companions close to these high luminosity, 10,000 solar luminosity, mass-losing stars. So we designed a project where we instead decided to go to Alma and look at stars that we know are binaries. So we thought that we could get away with 4, and we did. So we got time to do 4, and we selected them so that we would arrange in separation. So we have a close separation one, 10 AU, and then one that is at several hundreds of AU separation. And then for these two, we look at different wind velocities, because this will also make a difference in the shaping of the circumstellar envelope. So I will now show you the results that we have. So our query looks a lot more beautiful in H alpha than it does with Alma. But so this is the large structure that you see around this star. So this is a structure that is a minute, arc minutes across, so several tens of thousands of AU. It has this huge ring and these twirled jets going out like this. Now, if we zoom into this little box here, this is what the HST image looks like, but then they did it with sphere on the VLT. And they managed to resolve the two companions. So the two little black dots there are the two stars. So one is the AGB star and the other one is a white dwarf. And also make this pretty picture of the inner part of the jet. So with Alma, this is what we see. So this is the two stars again. So this image is the same scale as that image above. So here we see something that looks like a torus, a flattened distribution of molecular gas in the orbital plane. Now I don't have a nice picture of the velocity resolved information of this, but in a little bit lower resolution data, when you go through the different velocities and how they distribute themselves across this disk, we see some hints of that this structure actually is rotating. But so this is a case where the molecular gas is clearly affected by the hard radiation that will be in this region in here. So for this one, the distribution will not tell us so much about the mass loss rate history of the star, because we have photodissociation of the molecules messing up our picture. Myra is the next one. So you remember the beautiful galaxy image of Myra as it moves through the galaxy material is being ripped off, and it creates this huge tail. Now with Alma, we zoomed into this little box in here to look at the CO gas, and we get this crazy stuff. So you have to, here are the positions of the two companions again. So Myra A is closer to me, and Myra B is on the other side. So if we start with this one, what you see, which is complicated because you have to wrap your head around velocity and depth dimension, but I imagine it like a trumpet snail structure. So you're looking into the front of the snail here, and then it twirls around and makes like a spiral on the backside. And this is what you see here in these archy things here. So these are all the blue shifted velocities, so everything that is moving toward us, and these are all the red shifted velocities, so everything that is moving away from us. It's blown up here, we think, because of the wind that comes from the accretion disk of the companion. So this wind blows a hole in the molecular gas distribution. This is how we explain it. But in the case of Myra, this star is clearly affected by the history of the mass loss of this star. So it's not something that is easy to interpret. And also, of course, by the nature of the companion. This was the easiest one, W Aquila. This shows you, again, what you see at the center velocity. So imagine that you make a cut through the center of the star, and this is what it looks like. We have more gas flowing out to the southwest of the star, and there's a big arc going around like this. And there are also some archy structures within this flow gas. And we tried to do some 3D modeling of this. So this shows you now what a star with the same properties as this star when it comes to mass loss rate and wind and binary separation and everything that we know about it. If we let that evolve over time with an orbital eccentricity of 0.2, this is what the CO emission will look like. So we did like a 3D hydrodynamic model, and then we did 3D CO radiative, non-LT, non-local radiative transfer on that. And it comes out looking like this. And if you have a different eccentricity, you get this. So this has a larger eccentricity. And yeah, there was a little movie there to show you how this evolves over time. And we can do a pretty good job at reproducing this with this type of model. So even though we can't understand everything that goes on, we can at least reproduce some of the features that we see using the models. And then the largest separation source that I want to show you is called pi1 Gruis. And this is the only source where we see something that actually looks like it's going to turn into a bipolar PN. I wouldn't say that the other ones won't. I'm just saying that they're not there yet. They now still don't have a structure that looks like something similar to what we see in the planetary nebulae. So this is work that my student has been doing. He's been working on this source for his whole PhD thesis. And the channel maps are behind here, and they are complicated to understand. But what he has done is that he has built this structure in a 3D software that we have. And then you run radiative transfer on it, and then we can reproduce these channel maps that you see behind. And the structure that he needs to build to reproduce what we see in the different channels is something like this. So it has a slowly expanding torus, and then within this torus you have this kind of archy, spirally structure. So if you look at it from above, it looks like this. And then perpendicular to that, from the poles, we have this fast bipolar outflow, and for us fast is like 100 kilometers per second. So this structure is expanding at about 15 kilometers per second. And it's thicker, it's thicker towards the center, and then it thins out like this. Of course, doing 3D modeling, you can tweak, there's a lot of parameters that you can tweak. But to reproduce the velocity distribution that we see, there is actually not much variation that he can do to this structure and still manage to reproduce the data. So what did we learn from doing this project with binaries on Alma? Well, we learned that it's complicated. You don't get 4 different model pictures that you get from theory. The molecular gas structure will depend strongly on the nature of the companion and of also the history of the system. So like for Myra, for instance, we know that it has some outbursts every 1,000 years or so. And this will, of course, disrupt your structure and your flow of material. And I think the most important lesson, but also something that we really can't do much about, is that in order to directly reproduce observations with the model, you need to know the orbital parameters very well. And this we just don't have for these systems, because for the 400 AU separation one, that is thousands of years. So we will have to do with what we can get. So we're not quite at doing full 3D models of these systems yet, and maybe we will never be, but we can do complex models of bits and pieces. So we can reproduce these spirals, we can understand the wind evolution over time, you have to select some part of the structure that you try to analyze. We learn that a binary companion will clearly affect the wind distribution, so it will have a huge impact also at rather large binary separation. So the models show that you will only have an effect when you have very close companions, so tens of AU, but we get it even at 100 of AU, we still see a lot of impact from the companion. Okay, so I want to finish off with saying a few words about a project that I've started now. So this is a project that I call DEATHSTAR. I managed to make an acronym out of this long thing that sounds awesome. And a student made this beautiful logo as well. So this is, for many years, this was our main accomplishment. But now we actually have some results as well. So what we are doing is that we're doing 162 AGB stars, mapping them with Alma. So this shows you how they're distributed in galactic coordinates. This shows you the distance distribution, and this is the same plot as you saw before with the wind parameters. So it's the same sample as we have analyzed before, but the point of mapping it with Alma now is that we can constrain one of the main uncertainties that goes into these models that we do, where we estimate the mass loss rate, namely the photodissociation radius. So we get away from making an assumption by measuring it directly with Alma. The second aim of this project is to find these sources that seem to be binary or seem to have started to form planetary nebulae, so that we can study them in more detail. Because the 4 sources that we have done before are essentially the 4 ones that can be done with Alma in such detail, because they're close enough and they're in the south. All right, so so far we have analyzed 42 of the 100 observed sources. So these are 70 of them are done with Alma in the southern sky, and another 30 is done in the north with the Plateau de Bue in France. And we have a lot of data. And I'll just give you some tentative findings so far, because this is work that we're doing now. And what we find is that the sizes for the circumstellar envelopes that we assume are not correct. So when we measure them, we get a different answer, and this can impact the mass loss rate estimates quite substantially. And we also find that about a third of the sources are clearly not spherically symmetric. So this, and when I say not spherically symmetric, then I mean something that is so unsymmetric that you have to do it in 3D in order to be able to reproduce it. I mean, that it has, it's not, if you look at this R sculptoris type of spiral, that will not fit into this category, but it will have to be sources that are of this pi1 Gruitz type, where you have like a torus and a fast outflow or something like this, something that is clearly disrupted. But like I said, this is work in progress, so I'm hoping that I will come back and talk about it in, I don't know, I don't want to say a time. Thank you, that's it.
Okay, we have time for some questions.
Range in mass loss rates.
Yes.
Is most of the mass lost during the high mass loss phase, or is it lost in the low mass loss phases over long periods of time? What do you know?
We don't know. It's the best answer to that question. I mean, we don't have the time evolution. I mean, there is an answer from stellar evolution models. There is no answer from observations or wind models, really. I mean, you would expect it to be an increase over time, but it's going to be rather linear, like from the stellar evolution models now. We'll try to do this.
One of the more surprising results we got from a water survey with the SWAS satellite was the detection of water toward the classic carbon star IRC plus 10216.
Yes.
And it was 5 orders of magnitude greater, the water abundance, than was expected from models. Because it's carbon environment, so the thought was all of the oxygen would be locked in CO with very little left for water, but the water abundance was 10 to the 5th times higher. So we thought that was an anomaly. We went back with Herschel, looked at 6 other carbon stars, and found all of them had water emission. So I'm wondering, and the temperature of the water suggests that it's within a few stellar radii of the star. So I'm wondering if you've come up with an understanding of how that can be. I mean, how does that water form there? As you can tell from my question, I gave up. I had a theory, and it didn't pan out with the Herschel data, and I moved on. But
I mean, so there has been quite some debate about this water and where it comes from. I think the current understanding is that some molecules, not all of them, show different abundances than what you would expect from the equilibrium chemistry models. But you still, for both water and HCN, for instance, so you find a lot more HCN than what you would expect in oxygen-rich stars as well. But it's still a lot less than what you find in the carbon stars. And I think this is true also for the water currently. Like it's less than what you find in an oxygen-rich object, but it's still a lot more than what you would expect from equilibrium chemistry. So what people have been doing are these non-equilibrium chemistry models. And as far as I know, they are able to reproduce the abundances that you see. So you have shocks running through the inner, so like the day is just above the star, and this breaks up the CO molecules, and then you free up some water, some oxygen that you can use to form the water with. So this was part of my work on this sample, was to try to go through like all these parent molecules and molecules that are close to the star, and try to do it systematically for a larger sample of stars. And we got through to, I think we're on SIS and SO now. But for every molecule, the fewer stars we managed to so our sample shrinks with every molecule. It's difficult. I don't think we're done for sure. There's a lot of work now with Alma also trying to do higher sensitivity stuff to try to detect, like on a larger sample, to be able to say something more general than just this star has this crazy abundance or this star does not.
Okay, Roseanne, and then Martin, and then Margarita.
Maybe we all have the same question.
Yeah.
No, but I'm particularly interested in the star that would be accreting from these AGB stars. So I have 2 questions which I'll just ask and you can answer as you like. One is, I know in the case of Mira, as we actually discussed a little earlier, there is accretion even though the separation is something like 70 AU. Would you be able to estimate the fraction of the mass that's lost by the AGB and it's actually captured, or at least comes to the vicinity of the white dwarf companion? And then secondly, the mechanisms of accretion. I was wondering if the models of Shazrin Mohammed actually tell you a little bit about how accretion proceeds in an environment that is so complex as the ones that you're studying.
And so I'll try to start with your second question, even though it's not my own stuff. So the models that Shazrin has, so this is my collaborator Shazrin Mohammed. She's in Cape Town in South Africa. For the companion, she has a mass, a point mass. So anything that is related to the radiation field of the companion is not included in these models. So that, and this will, this is a lot of work still with what she has, and this is something that she's planning to do, but we're just not there yet from theoretical side. And this will clearly have an effect on what you can accrete or what, because you will have some radiation pressure from that one as well. So it's not so easy. I think we actually have even higher resolution data on Myra with Alma, which I didn't show today because it's not published yet. Maybe with that data we could constrain it by comparing it to the models as they are. I mean, that will give you something that is rather uncertain, but it will be, I don't think the spatial resolution of this data that I showed today is good enough to do something like this.
Martin? Yes. So I understood for a long time the folklore has been that AGB stars dominate the dust production in the galaxy. I wondered if your new mass loss rates say that's correct or not. Change the picture.
I think we know. I mean, I'm on thin ice. I think that we have a pretty good idea of how much dust the AGB stars produce, for sure. I don't know if we know. I mean, I think the problematic part is perhaps how much dust the higher mass stars produce. So to say whether they dominate or not is not so easy. But they do. I mean, so they do produce a lot of dust. To say something very vague. Sorry.
Margarita?
Comment and a question. Relating to Roseanne's question, Shazreen, Mohammed, and also Miguel de Balboro, two groups that have been doing this row slope overflow accretion, and it compared to the regular bonding coil, is at least 10 times higher the deposit of mass on the accreting companion, even if they are kind of detached with 100 astronomical units away from each other. So it will be very interesting whether experimentally one can prove that or not. But the question is that I had was on the other query, those beautiful Alma data that you have. So you have one is the lines here and one is the continuum. In one of them, so it's a disk, they say, which is very impressive. But you say when one of them shows on this side more, and then the high resolution Alma shows a little bit asymmetry on this side. You can go back to that image, maybe you can comment from that. How do you understand that? Right.
You want that one?
Yeah, those two at the bottom.
I mean, this is the same type of data. These are both CO data. This is slightly higher. So yeah, I didn't include the beam here. This is the beam of this data. So it's a very high resolution. This is about, here the beam is about 0.25 arc seconds or something like this for this data. So this is lower resolution data. And I don't have the velocity resolved image for this, but I have it for this because this is my own data. And what I see when I step through the velocities is that so on the front side I have something on this side. These are the blue shifted velocities. And then in the red shifted velocities I see emission on that side. So in principle you could have, so this could be a rotating structure. But the problem is that you get something similar if you have an expanding. So we try to explain this in the paper that if you have an expanding structure, you can get the same thing because it depends on the orientation that you're looking at it from. So it's a bit degenerate depending on the orientation. I think that if we now with this data, when we know that it's like that, it really looks like we're looking at an edge on disk, then I think that we can probably infer that it is rotating, but I would have to investigate this data before I can say for sure. And I haven't done that yet.
Yeah, if you look at your next slide, I think it's Myra. Correctly?
Yes.
Yes. It's a beautiful, seal swirl.
Yes. It's a heart.
Yeah. I was wondering if you have considered, and I don't know if this is relevant for this at all, the possible effect of UV and X-ray photons in exciting the CO and causing some of these holes you see here.
Yes, so we did a back of the envelope calculation, given what we know about the companion, whether this hole could be due to photodissociation instead, and that structure would be a lot smaller than what we see. While this is consistent, this is also a simple estimate but it's more consistent with the wind properties that have been measured. So from the companion has, or the accretion disk around the companion has a solar type wind, so 10 to the minus 14, 400 kilometers per second type of wind. And then that fits with the size of the hole that we see. Yeah, so.
And I guess as a corollary, that's for you. Do we have Chandra images of this guy?
Of Mara, yeah,
Yeah.
definitely.
Yes,
We're
when
doing
we
this
see
together.
flow between the two stars, their companion,
So you
famous
see-
press release,
yeah.
yep. But the
Yeah.
surrounding, of course, we don't see extended emission, but we do have in the central region there and show this overflow between the two dots, showing the Chandra resolution.
So in the higher resolution mirror images that I unfortunately cannot show today, what we see is the same type of flow that Margarita sees in the Chandra images, and then we also see material being flung out behind the companion. So in this thing here, when you look at it in high resolution, you see it breaking up into clumps of material. Yeah.
Andrew?
Okay, you mentioned at the beginning that these winds are driven by radiation pressure
Yes.
on the grains.
Yes.
But what gets the material out there from the surface of the star? Do you just assume it's there, or do you
No.
have magnetic fields, or do you have pulsations, or what? How do you?
I mean,
get it
we
out there?
have, so the traditional models, we have like the star is supposed to be pulsating. But actually, when they do this when they do these star in a box models, then the convective movements is actually enough to throw out material outside of
So you
the
assume that
star.
those bright spots are convective spots that
Yeah.
then are moving material out
Yes, so
to
these are
several stellar radii.
yes, so these are like these giant convection cells that you get from just solving the hydrodynamics of the whole star, and then those are so large that they will like disrupt the whole star like this, and this is just what you get from the calculation.
Okay.
And then these movies shows you where the conditions for dust formation are fulfilled. So here you have dust, and then the temperature will, as the star bubbles, the temperature will change with radii, and this dark region is where it's too hot for the dust to exist. So these dark blobs are just hot regions where the dust is destroyed.
It just is destroyed.
Yeah.
You mentioned that the gas-to-dust ratio has changed substantially. Is the hot material mixed in with the cold material, or is it clumpy, or is the cold material clumpy and the hot material more diffuse, or do you have any sense of the mixture?
I mean, so for the circumstellar material, it's cold enough to essentially be in molecular form, all of it, and it's clumpy. I mean, it's for sure clumpy. And how clumpy it is something that we're trying to figure out now with these new result observations that we're getting. But we only have Alma for a couple of years, so.
Okay.
I think we have to wrap up, unfortunately, now. But Sofia will be here. Let's thank her again. Do you want to join us for dinner?
Yeah.